Okay, here's another quick little video on fluid dynamics. I'm a very curious person, and one day I took a Frisbee into the swimming pool and I dragged it in this direction, and I was startled by what happened. The orientation that the Frisbee took with the fluid flow was startling. So go ahead and pause your video and try to figure out what the Frisbee is going to do if I literally grab it like this and pull it this way. What is the Frisbee going to do? Okay, so here's the orientation that the Frisbee will take. You can try this at home in a swimming pool or whatever. So it turns out it does not matter what this shape is. The only thing that matters is what direction the water leaves the trailing edge. So in this case, the water leaves the trailing edge in this direction. And the water on the other side goes this way, and it leaves in that direction as well, and you have a circular vortex here. That causes the Frisbee to rotate approximately 45 degrees. And even if you're pulling here, it will rotate that like that. It's just kind of nuts. And when I discovered that, I realized the shape doesn't really matter. What matters is where's the flow coming off the trailing edge of any surface. And that really opened my eyes to the design of a stern on a boat. Here is the design. This is the stern. So the front of the boat is over here, and this is literally the midpoint of the boat. And the boat travels this way. So this is the stern of the boat. This is my shuttle punt prototype, which I just sailed for the first time a couple weeks ago. And I went ahead and measured an angle measurement tool, the precise angle at which water is leaving my stern, and it turns out to be 15.8 degrees upward. So if you watch the video, you'll notice that water shoots like this. That's a problem right there, all that water shooting up. And it lifts all this water above the water line here, and it creates this big wave, and that creates drag. It is minimized slightly by the bow lifting slightly, but because the boat is 12 foot long, the bow is not going to lift all that much. So that is what is currently happening with my current shuttle punt when I put a sail on it and go over the length waterline formula speed limit. So it's 5.1 miles per hour is my current speed limit. If I'm just paddling as hard as I can go up to 5.1. With a sail, excuse me, with a sail I can go to about 8 miles an hour, which is about 7 knots. This is what I did with the plans for the shuttle punt 1 and 2. They're both basically the same. I basically doubled the height of the stern, and I cut this angle in half. So in this case, the water would go like this, and it's not going to lift as much water, and the boat will be faster. However, I'm thinking about creating an even better stern for my sailing punt, and here are two stern options. This is the most typical one. It's you can find this on a laser boat, in a weta trimaran, and windsurfing boards. They have a very, very slight angle, upward angle of 2 to 3 degrees. And the problem with this is at rest, the stern is usually below the waterline slightly. depending on the boat and how much curvature it actually has. And this is my proposed design. So what I have done is I've created an S shape, and it's still rising about 2 degrees off the end, but it will literally create just this much. That's how much water will be lifting off the stern. And because okay, so the difference between these two is, okay, so if this is going really fast, this hull will lift out of the water more than this one. However, this one has a skimming disc AMA, so that will actually help lift this higher up out of the water. The other thing it does is it creates pitch stability. So if you look at the vector, this vector, it kind of, if you extend it forward, it goes a little bit more through the center of the boat than this one. So with this configuration, you get a little bit more lift in the front of the boat. But in my case, I don't really need lift in the front of the boat because I put the skimmer in line with the sail, so the boat won't, the sail is not able to cause the bow to dig deeper into the water. So anyway, the disadvantage of this is, you know, if you overload the boat, then this sinks under the water. So that's why the shuttle punt 1 and 2 is a good medium design. It's not ideal for fast, but it's also better than this one, which is only good for slow speeds, and this is good for slow to medium speeds, and this is good for speeds that are basically planing speeds above 5 knots, 5 to 10 knots, which is what I hope to achieve with my shuttle punt with a sail rig. I've already gone about 7 knots, and I really think this drag is what's causing me from being able to go above that and hit 10 knots, which is kind of my goal for this sailboat. And one more point, because now we discovered that the direction and rotation of the boat is determined by the direction at which the flow leaves the transom. This is a top view of a asymmetric hulled catamaran, and indeed, if you bisect this angle, the water will leave the leeward hull in this direction, which, if you extend this vector forward, it's a lot more in the middle of the boat than if the vector was going this way. So this does help the boat from going downwind because it literally has it's actually pushing kind of like, so if the water's flowing this way off the trailing edge, then it's kind of, you can kind of imagine that it's having this effect. In other words, if you remove this hull, this would want to go this way, but also rotate that way because it's this vector is on this side of the center of mass of this object. But when you have a catamaran, your overall center of mass is somewhere between here and here, and that's I really think that this works ideal when this hull is lifted but not completely lifted out of the water, because then your center of lateral resistance might move here, and if it's in line with this vector, then you get 0 rotation, but you do have a vector going in this direction that resists leeway. So I think the problem with the Hobie 16 is when this hull is completely flying, and the vector wants to turn the boat this way, and you can't overcome that rotational force. That's why they kept pushing the sail backwards on the Hobie 16. I don't know if you knew this, but the sail rig has been moved back twice, and they do this by angling the sail backwards. The original Hobie 16 looked something like this, and I think it was like somewhere in the mid-80s they changed the angle of the mast like this, and then they changed it one more time to be even more canted backwards. And they did this by just instead of changing any molds or production parts, they just changed the length of these side stays and forestays. So if you have a really old Hobie Cat 16, your sail is going to be, your mast is going to be more vertical, and if you get a new one, it'll be a different angle. This, I don't know what this angle is, but they changed it twice, and that was because the problem of it wanting to at very high speeds rotate away from the wind. But the premise of asymmetric hulls, it has merit. It's just it works in a very limited fashion. And if you add a rudder here, you're taking all this water and you're redirecting some of it, and it's going that way. So you kind of kill the whole purpose of the asymmetry by having a rudder. So if I was going to design a proa, I would basically not have a rudder. I would design it so that the sail could lean forward or back, and that's what would cause the boat to turn. And then having a hull like this would be more effective.